Math Day, great day, Math Day learners. Welcome to the Mathematics Lay channel where we turn your math worries into mastery. I am Andre and together let us have fun while learning. Today we're going to unlock one of the coolest ideas in algebra, which is how to understand, describe, and interpret the graphs of polynomial functions. But by the end of this lesson, you'll able to look at an equation already know that the attitude of its graph even before drawing it. Now, have you ever look a math graph and thought, how I am supposed to know what this curve is doing? Well, today, you'll discover something powerful. Polynomial graphs are predictable, and once you learn the patterns, you can understand their behavior instantly. So, let's break it down in the simplest, easiest way possible. Ayun yung intro. Tapos, for our learning objectives, at the end of this lesson, the student should be able to first understand the meaningful and characteristic of polynomial functions, describe the end behavior, turning points and roots of polynomial graphs, and lastly, interpret the graph of polynomial function using degree, coefficient, and intercept. And it'll show you different polynomial graphs. You will identify which graph doesn't not belong. This one. Our engaging activity, you will identify the graph doesn't belong in a polynomial function. Is it this one or this one? So, the one with the sharp corner or break is not a polynomial. Today, we're going to find out why polynomial graphs are always smooth and how their shapes follow predictable patterns. Constant function degree 0. This graph is just a horizontal line. No matter what x value you choose, the output stay the same. Graph behavior will be a flat line, no turning points, no slope. Next, we have the linear function degree number 1. This graph is diagonal, either slanting up or down. Graph behavior will be looks like a straight line. Now say hello to the quadratic degree number 2. This one of the forms a parabola, a curve U shape. This graph behavior have turning point, a maximum or minimum, symmetrical, opens upward or downward, linear function change at a constant rate. Next we have the linear function. Now, the cubic function degree 3 starts getting interesting, right? It has curve value, a twist sometimes, crossing the x-axis more than once. Graph behavior will be can have an S-shape up to 2 turning points. Ends go in opposite directions, one up and one down. Quadratic give us the classic curve value, bola. Now the quantic function degree 4. This graph looks like a double parabolas. They can wiggle even more. Graph behavior up to 3 turning points. Ends go in the same direction, both up or both down. Quantics can have double dips. And lastly, the quantic degree 5. This one can twist several times and has the most complex shape among the first 5 degrees. Graph behavior up to 4 turning points. Ends go in opposite direction. Very flexible shape. Quantics wiggle the most. Now, our activity will be draw a simple rough sketch or of degree 1 function, a degree 3 function, a degree 4 function. Then, we will label each graph with its degree. The first one is degree 1 linear. For example, f of x or f of x is equal to 2x plus 1. The shape is straight line because f of x is only to the power of 1. The rate of change is constant. It doesn't accelerate or curve. It just goes up or down steadily. Turning points, 0, a straight line never turns around. The end behavior go in opposite direction. If it starts down on the left, it goes up on the right or vice versa. Next, degree 3 cubic. Example, f of x is equals to x cubed minus 3. The shape, an S-curve or snake. Opposite ends because 3 is an odd number, negative number stays negative. Negative 2 raised to 3 is equals to negative 8. And positive number stays positive. 2 raised to 3 is equals to 8. This means the graph generally starts low and high or vice versa. The wiggle the curve happens because the different terms fight each other. In x cubed minus x, then x cubed pushes up very fast but near to the center. The negative x pulls it down, creating a hill and a valley. Turning points, the maximum number, it can be 2, it can go up, turn down, and turn back up again. And lastly, degree 4 quartic. Example, f of x is equals to 4 raised to, no, x raised to 4 minus 2x raised to 2. The shape will be a W or U shape. Same end because 4 is an even number. Negative inputs became positive. Negative 2 raised to 4 is equals positive 16. This means both ends of the graph point in the same direction, usually both up. Complex curve with a degree of 4, the graph has enough complexity to go down, turn up, turn down, and turn up again. Turning point, the maximum is 3. Notice the pattern. The maximum number of turns is always the degree minus 1.
Same end because 4 is an even number. Negative inputs became positive. Negative 2 raised to 4 is equals positive 16. This means both ends of the graph point in the same direction, usually both up. Complex curve with a degree of 4, the graph has enough complexity to go down, turn up, turn down, and turn up again. Turning point, the maximum is 3. Notice the pattern. The maximum number of turns is always the degree minus 1. For our developing competency, we will have a short activity. Now get your pen and paper once again and let's test if you really understood our lesson. Our activity will be scenario matching. Below, our real-life situation match each situation to the most likely polynomial's degree 0 to 5 based on the shape shown in your image. Our situation will be a car moves a constant speed on a straight way. Lastly, the height of a ball throw in the air, it goes up, slows down, then falls. Third, the profit of a company over time that rises, dips slightly, then rise again. Fourth, a roller coaster track that goes up, down, before stopping. Fifth, a person bank saving when they don't deposit or withdraw anything. And lastly, a temperature pattern that decreases again, and then increase multiple fluctuation. And these are the answer. Thank you for listening. Bye-bye.